Dear students, welcome to the fourth session of our Chapter 4 Chemical Kinetics. Today we will deal with the topic half-life of a reaction. How we can define a half-life of a reaction is the time in which the concentration of a reactant is reduced to one half of its initial concentration. That means in what time the concentration of the reactant is getting reduced to half from the initial concentration is said to be half-life of a reaction, and it is represented as T half, T 1 by 2. And for zero order and first order reactions we have to calculate the T half. Let's now discuss about the zero order reactions half-life. We know that zero order reaction is having a rate constant and it is given as K is equal to R0 minus R by T. If we are taking the time T half, automatically the R becomes what? Half R0. Initial concentrations, half it is getting reduced. So it will be R0 by 2 or 1 by 2 R0. If we substitute this value in our zero order rate equation, then we can write K is equal to R0 is as it is written minus, instead of this concentration of R, we can write 1 by 2 R0 by time is T half. Now, after calculating, you will get what? R0 by 2 T half. The K value you are getting. Just replacing or rearranging the equation, we will get T half is equal to R0 by 2K. Now here, this is our half-life for a zero order reaction. And from this equation, it is clear that T half for a zero order reaction is directly proportional to the initial concentration of the reactant, and it is inversely proportional to rate constant. With this equation, we can understand that R0 is directly proportional and K is inversely proportional to half-life of the zero order. Next, we will see the first order reactions half-life. And first orders half reactions, when we were learning, we learned to write the rate constant as 2.303 by T log R0 by R. And if we change the time to T half, automatically the molar concentration of R becomes R0 by 2. So if we substitute these two values in the rate constant, first order rate constant equation, it becomes K is equal to 2.303 T half log R0 by R0 by 2. And we know that these two gets cancelled and you will get this 2s in the numerator. So it becomes T half is equal to 2.303 K log 2. And log 2 is 0.301. The value is there which we can learn. So it is T half is equal to 2.303 by K into 0.301. And it's again the calculated value T half is equal to 0.693 by K. And this is our rate, first order rate constant, how it is changed into T half. So this is what T half is equal to 0.693 by K. If we want the rate constant, we can write it as what? K is equal to 0.693 by T half. Thus, for a first order reaction, half-life period is constant. That is, it is independent of the initial concentration of the reacting species. We can't see here the molar concentration of the reactant. So it is said to be what? The half-life of the first order reactions are independent of the initial concentration. Now next topic is pseudo first order reaction. The word pseudo means false. That means something, it is not the correct one. Reactions which are not truly of the first order, but under certain conditions it become that of the first order, are called pseudo unimolecular reactions, or we can say it as first order reaction. Let us see an example hydrolysis of ester in the presence of acid CH3, COO, C2H5. Ethyl acetate plus water gives ethanoic acid and ethanol. This equation we have learned before also. So it is what? Hydrolysis of ester. If for this reaction we want to write the rate expression, how we will write? A rate is equal to K into molar concentration of CH3, COO, C2H5, that is ester, into molar concentration of water. Since hydrolysis takes place in the presence of excess of water, the concentration change of water is negligible practically. So we don't want this term at all. So we will write that rate is equal to R dash ester, molar concentration of ester only. That is water we are neglecting. So it is what? R is equal to R dash. What is that R dash? R dash is K into water there. Or simply we can say right now the rate constant is depending upon only one concentration. Even though two reactants are there, only one reactant is involved. So it becomes what? First order. So this type of reactions are said to be pseudo first order reaction. Integrated rate laws for the reactions of zero and first order. We can just place them in a chart and see the difference. We can see here a table where it has order, reaction type, differential law, rate law, integrated rate law, straight line plot, half-life, and the unit of rate constant. For the zero order, the reaction type is just written R gives P. And the differential rate law can be written as d of R by dt is equal to minus K. Integrated rate law, how we can write? Kt is equal to R0 minus R, or it can be K is equal to R0 minus R by T. Then what about the straight line? R versus T. If we plot molar concentration versus time, we will get a straight line. And half-life of the zero order is Tf is equal to R0 by 2K. What is the unit of rate constant for zero order? Mole per liter per second. And what about the first order reaction? The reaction type is R gives P. But when we write the differential rate law, we can write d of R by dt is equal to minus K of molar concentration of R. Integrated rate law, when we are writing, we can write it as what? Kt is equal to ln R0 by R. Straight line plot we are getting for which case? We are getting for ln R versus time. And the half-life is given as ln 2 divided by K. ln can be converted into log of 2.303 when we are using. So when you multiply that one with this value, we'll get what? The value of 0.693. Right? Then we can use the term 0.693 by T half, or the K value you can put. T half is equal to 0.693 divided by K. Then what about the unit of first order? It is second inverse. Now we can have a look on the graphical representation of the first order, zero order, and second order plots. Now see the first diagram or first graph where we can see dx by dt. That is the rate with concentration for the zero order. And you can see here a straight line which is what? Which is just what? A constant line we can see with time or with concentration. Second one, you can see increase is there. Dx by dt with the concentration for the first order, increase is there. For the second order also, the graphical representation when you plot, you can see increase with the concentration, you can see. So this is what? A graphical representation of rate versus concentration. Now the second graphical representation is representation for concentration of integrated rate equation versus time. Concentration of integrated rate equation versus time. Here for the zero order concentration of A versus time when you plot, there's a decrease. Then for the first order, you can see log A by T versus T, you can see again a decrease is there. What about the second order? 1 by molar concentration of A versus T, when you plot, there's an increase with an intercept. Right? This is the graphs for concentration of integrated rate equation versus time. And the last one is the graphical representation for half-lives versus concentration. For the zero order half-life versus concentration, it is a increase. For the first order, it is what? Constant. It is independent of the concentration. That's why. Then, what about the second order? Again, increase is there, but with the intercept. So these are the graphs for the graph representation for the half-life versus concentration. Topic is temperature dependence of the rate of a reaction. Most of the chemical reactions are accelerated by the increase in temperature. For a chemical reaction, with the rise in temperature by 10 degree, the rate constant is nearly doubled. The temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation. And the Arrhenius equation is given as K is equal to A into e raised to minus Ea by RT. K is equal to A into e raised to minus Ea by RT, where this capital A is said to be the Arrhenius factor, or we can name it as frequency factor. It is also called pre-exponential factor. It is a constant specific to a particular reaction, where R is a gas constant and EA is the activation energy, which is measured in joules per mole. It was first proposed by Dutch chemist J.H. van 't Hoff, but Swedish chemist Arrhenius proved its physical justification and interpretation. Next, we will deal with the Arrhenius theory. It explains that the products are formed through the intermediates or the activated complex. This can be understood by the following reaction, that is, the reaction between hydrogen and iodine. Hydrogen plus iodine giving 2Hi, hydrogen iodide. Now, in this reaction, how is the formation? You can see here HH plus II gives you an intermediate complex, where the same weakly bonded bonds are there between the hydrogen Hi, II and Hi also. After some time, it just breaks this bond and the formation of 2Hi is there. So this is a intermediate compound which is what? Unstable also. According to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. It exists for a very short time and then breaks to form two molecules of hydrogen iodide. The energy required to form this intermediate, called activated complex, is known as activation energy. A graph is plotted versus potential energy and reaction coordinate. Here H2 plus I2 is the reactant and the product is 2Hi. Before this reaction, an intermediate compound is formed or the activated complex is formed. To the energy required to form this intermediate is called the activation energy, EA. The reaction coordinate represents the profile of energy change when the reactants change into products. Now we can have the determination, or how we can find the activation energy. It can be determined by graphical or the numerical analysis of activation equation. Next, we have the graphical method to find activation energy. In the Arrhenius equation, the equation is what? K is equal to A into e raised to minus Ea by RT. The factor e raised to minus Ea by RT corresponds to the fraction of molecules that have kinetic energy greater than activation energy. If we take the natural logarithm of both the sides of the equation, we'll get this equation as what? Ln k is equal to minus Ea by RT plus Ln k. And if we plot a graph, Ln k versus 1 by t, it will be a straight line according to this equation. And through this, we can understand the slope is what? Minus Ea by R, and the intercept is what? Ln A. And then we can calculate what? Ea and A using these values. So activation energy can be found through the graphical method. Thus, it has been found from Arrhenius' equation that increasing the temperature or decreasing the activation energy will result in an increase in the rate of the reaction and an exponential increase in the rate constant. Next is the numerical method to calculate the activation energy. Now, if we have the temperature T1, we can have that equation ln k is equal to minus Ea by RT plus ln as what? Ln k1 is equal to minus Ea by R T1 plus ln A. If temperature 2 we are having, T2 we are having, we can write the equation as ln k2 is equal to minus Ea RT2 plus ln A. These two equations we have taken as 1 and 2. Now, K1 and K2 are the values of rate constants at the temperatures T1 and T2 respectively. If we subtract the equation 2 from equation 1, we'll get ln K2 minus ln K1 is equal to Ea RT1 minus Ea RT2. So this is just exchange so that it becomes what? The form of minus. Otherwise it should be in plus form, or this should be in reverse. So ln K2 by K1 can be written as what? Ea by R, and these two are taken common. Then inside the bracket what we will write? 1 by T1 minus 1 by T2. Then log K2 by K1 can be written as what? In the form or the ln is changed into log. So we will write what? Ea by 2.303 R into 1 by T1 minus 1 by T2. Again, if we rearrange this equation, we can write log K2 by K1 is equal to Ea by 2.303 R T2 minus T1 by T1 into T2. These two equations we need for our problems if the activation energy is to be calculated. Now the next topic is effect of catalyst. What do you mean by a catalyst? It is a substance which increases the rate of a reaction without itself undergoing any permanent chemical change. So remember this definition. What do you mean by a catalyst? It is a substance which increases the rate of a reaction or increases the speed of the reaction without itself undergoing any permanent chemical change. We are giving an example of manganese dioxide. If it is a catalyst, manganese dioxide is a catalyst, how this reaction changes? 2KClO3 gives, in presence of MnO2 as the catalyst, it changes into 2KCl plus 3O2. It increases the speed of the reaction. If the word catalyst should not be, or if the word catalyst we are using, it should increase the rate of the reaction. But if it is doing in the reverse order, that means it is not increasing the speed of the reaction, instead it is reducing the rate of the reaction, then we can't say the word catalyst there. So we want a new word there for that substance. It is said to be inhibitor. If it is not increasing the rate of the reaction, instead it reduces the speed or the rate of the reaction, we can name that substance as inhibitor in that reaction. The action of catalysts can be explained by the intermediate complex theory. If, according to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. This has a transitory existence and decomposes to yield products and the catalyst. We are explaining a reaction. Your potential energy versus reaction coordinate we have explained. Reactant is here and the product is there. So before that, what is there? An intermediate complex or intermediate is there, which is said to be activated complex. And reaction is shown here. A, B, and here what? Activated complex C is there. Now you can see here, if the reaction is there with the presence of a catalyst, how is the path or how is the speed of the reaction we can see. Now first you can see here the graph or this path. Reactant gives product. What about the energy? The energy of activation without the catalyst. You can see here this much energy is used. That is reactant to the complex or the intermediate. How much energy is required to form this catalyst intermediate compound? That energy is said to be activation energy. Without the catalyst, how much it is? This much. If you use a catalyst, then the path becomes or this height becomes small. That is, the activation energy with the catalyst is less. If this diagram you can understand, we can clearly say or prove that with the presence of a catalyst, the reactions rate is getting increased. The both the diagrams you can see with one in the catalyst present and the other one without the catalyst. So with this we can understand the presence of catalyst increases the rate of a reaction. Next is the collision theory of chemical reactions, and it states that for a reaction to occur, the reacting molecules must have, first point is, the energy equal to or greater than the activation energy. And the second point is the reacting molecules must also collide with correct orientation. If these 2 points, if the reacting molecules are not obeying, then the reaction cannot occur. The collision in which the molecules collide with proper orientation and kinetic energy, which is equal to or greater than the activation energy to break the existing bond between the reacting molecules and to form the new bonds to form products, is called the effective collision. So, the collision, that means the collision in which the molecules collide with proper orientation and the kinetic energy, which is equal to or the greater than activation energy to break the bonds and to form new products, is said to be effective collision. Therefore, for a product to be formed in a reaction, we have to take these factors into consideration. And the rate constant of a reaction can be expressed as K is equal to P into Z into e raised to minus Ea by RT. It is the Arrhenius equation itself. But the thing is, in Arrhenius equation, we have written K is equal to A into e raised to e minus A by RT. But instead of A, right now we are having here P and Z. Now what does this P and Z represent? We'll see. Where P represents what? The steric factor. That is, it reflects the fractions of the collision with correct orientation. And Z represents the collision frequency. It is the total number of collisions per second. So this is what the effective collision, where we are having the rate constant as P into Z e raised to minus A by RT. Thank you, and we are concluding this chapter.